We now know how to draw quite a variety of shapes. We know how to draw straight lines. We know how to draw parabolas. We know how to draw cubic graphs. We know how to draw power 4 graphs. We know how to draw reciprocal graphs. If we have a set of axes, a 1 over x curve, looks a bit like this. We know how to draw 1 over x squared curves, looking a little bit like this. What we may have to do is to analyse situations where these curves intersect and to see what that can tell us about the solutions of related equations. Here's a straightforward example which will explain what we have to do. In the first part we're asked to sketch the curves y equals x squared and y equals 1 over x on the same set of axes. Both of these are curves that we understand well. The graph of y equals x squared looks like this, and the graph of y equals 1 over x looks like this. It has asymptotes of both the x and y axes. In part B, we're asked to state the number of solutions of the equation x squared is 1 over x. How can the diagram help us with that? Well, if we have just sketched a graph of y equals x squared, and a graph of y equals 1 over x, then those graphs will intersect at the points where x squared is 1 over x. So therefore, every solution to this equation is a point of intersection of those two graphs. Well, it is very easy to see that our two graphs have just one point of intersection. Even if we have not drawn these absolutely perfectly, the general shapes and general positions are correct, so the fact that there is only one point of intersection means that there is only one solution to that equation. Therefore, for part B, we could say that because there is just one point of intersection, that means that there is only one solution to the equation x squared is 1 over x. In part C, we're asked to solve that equation. This is the same thing as finding the point of intersection. These questions could be asked in either way, solve the equation or find the point of intersection, and it's always best to do this algebraically. So, in part C, if we have that x squared is 1 over x, we can multiply both sides of the equation by x to get x cubed is 1. That only has one solution, which is x is equal to 1. Because we've only been asked to solve the equation, that's the end of the story. But, of course, we can see that whichever equation we use, an x-coordinate of 1 would give a y-coordinate of 1, which means the curves would intersect at the point 1, 1. And if we return to our graph and show the values on the axes, we can see that the point of intersection of those curves is indeed 1, 1. Now, the previous example was quite straightforward to show the ideas of this particular topic. This one is a little more challenging. Now we have to sketch the curves y equals x squared plus 2x and y equals x cubed subtract x squared subtract 2x on the same set of axes. So we have to use some of the methods we previously used when graph sketching. Let's start off with y is x squared plus 2x. Well, we could rewrite that in a factorized form as y is equal to x into x plus 2. From here, it is easy to see that if y is 0, then we will have an x of 0 or an x of negative 2, and that gives us intersection points of this curve with the x-axis of 0, 0 and negative 2, 0. This is a quadratic curve with a positive coefficient of x squared, so it has this general shape. So showing our points of intersection, and from our general knowledge of the shape of the curve, we know that it looks like this. Without doing a little more work to find the vertex, we don't know exactly what this curve looks like. It could have a vertex which is higher up or lower down than this. But we do know that this is the general shape of the curve. Whichever one of these positions the vertex takes, we've got a general sketch. Let's now return and look at our other curve. Our other curve is y is x cubed, subtract x squared, subtract 2x. We can again factorize an x out of that, so y is x into x squared, subtract x, subtract 2. And it's not too difficult to factorize that quadratic factor on sight as x subtract 2, x plus 1. So the intersection points of this curve with the x-axis are again 0, 0, 2, 0, and negative 1, 0. This is a cubic curve with a positive coefficient of x cubed, so we know that it has this general shape. We have already plotted the point of intersection 0, 0. If we plot the other 2 points of intersection, then using our understanding of the shape of the curve, we know that it looks like this. Once again, we don't know exactly how high up or down this curve goes. It could be any one of these curves if we stretch it in the y direction, but the general shape is correct. In part B, we're asked, giving a reason, state the number of solutions of the equation x cubed subtract 2x squared subtract 4x is 0. Well, that equation did not appear in part A, but it's quite easy to see that we do get that equation by combining the 2 equations we have got in part A. Let's be a bit clearer about that. If we have got the curves y is x squared plus 2x and the curve y is x cubed, subtract x squared, subtract 2x, then at the point of intersection we will have the x cubed subtract x squared subtract 2x is the same as x squared plus 2x. Bringing everything onto one side, we have x cubed. Now if we subtract an x squared from both sides, we'll have negative 2x. If we subtract 2x from both sides, we'll have negative 4x. That's all going to be equal to 0. So therefore, this is the equation which is satisfied at the points of intersection of the curves. And from our sketch, we can see the number of points of intersection. We have 1 down here and 1 here. That's 2. But we need to be a little bit careful here. The x cubed curve will increase more rapidly than the x squared curve. In other words, if we look a bit further up, there will be another point of intersection. We could also see this just by zooming out on the curves until we can see enough of them. Now, even if you were to draw just these parts of the curve that we could easily see, then it should still be clear that the further and further up we go, there will eventually be a third point of intersection. And so we can now answer part B. We can say that because there are 3 points of intersection, that will mean that the equation has 3 solutions. In part C, we're asked to find those solutions, and again we should proceed algebraically. We have the equation x cubed subtract 2x squared subtract 4x is 0 to solve. We can factorize out an x from that, giving us x into x squared, subtract 2x, subtract 4 equals 0. Now this quadratic factor, are we going to be able to factorize that? I can't see an easy way to do it. Let's just quickly check its discriminant. Its discriminant is b squared negative 2 squared, subtract 4, subtract a, which is 1, subtract c, which is negative 4. That is going to give us 4 plus 16, which is 20. Now the fact that this is greater than 0 means that it does have 2 solutions. Of course we already know that because there are 3 points of intersection and we need to find 3 solutions. But this is not a square number, so this is not going to factorize. Because of the fact that x into x squared minus 2x subtract 4 is 0, we know that either x is 0 or x squared subtract 2x subtract 4 is 0. So how are we going to solve this? I think I'll complete the square on this occasion. You could use the formula, various ways we can do this, but completing the square we have x subtract 1 squared subtract negative 1 squared subtract 4 is 0. So that means that x subtract 1 squared subtract 5 is 0. So x subtract 1 squared is 5. X minus 1 therefore is plus or minus the square root of 5, and adding 1 to both sides we have that x is 1 plus or minus root 5. So our final conclusion is that the solutions are x is 0, x is 1 subtract root 5, and x is 1 plus root 5. And on our diagram, the x equals 0 is this point of intersection. The x is 1 minus root 5 would be the x coordinate that goes with this point of intersection, and the x is 1 plus root 5 would be the x coordinate that goes with the point of intersection of the curves, which is, on this diagram, way up and difficult to see. In this example, the curves we have to work with are a little more challenging. Let's start off by looking at y is negative x plus 1 x subtract 2 squared. Well, this is a cubic equation, and it's not difficult to see that its points of intersection with the x-axis are negative 1, 0 and 2, 0. But the 2, 0 is a repeated solution. Also, we have a negative coefficient of x cubed if we were to multiply all this out, so we know that our curve has this shape, and our repeated solution is a place where the curve just touches the x-axis. So plotting our points of intersection, we can sketch the curve using our knowledge of its general shape and the fact that the point 2, 0 is where the curve will touch the x-axis. Notice that the curve cuts the y-axis at negative 4, 0. That would have been very easy for us to discover, but isn't important for what we need to do here. We just need the general shape. Our other curve is a little more challenging. We have to sketch y is negative 1 over x subtract 3. Well, we could obtain this curve from one that we do understand. Y is 1 over x. If we were to replace y by negative y, we would have negative y is 1 over x. So we have gone from a y to a negative y, which means with our transformation work that we have to do a reflection in the x-axis. And then if we replace the x by x minus 3, in other words, so the x changed to an x minus 3, that means that we have to do a translation of 3, 0. And this final curve, negative y is 1 over x minus 3, that's the same as y is negative 1 over x minus 3. So here is how we can get the curve we're trying to sketch from one we understand, reflect it in the x-axis and translate it 3 units to the right. Well, those two transformations can be done independently of each other. In other words, it doesn't matter which order we do them in. So let's begin by taking a graph of 1 over x and translating it 3 units to the right. The asymptotes of the original 1 over x curve are the x-axis and the y-axis. If we translate them 3 units to the right, the x-axis is still mapped to the x-axis, whereas the y-axis would have been translated to the line x equals 3. Using the x-axis and the x equals 3 line as our new asymptotes, this is a graph of y equals 1 over x minus 3. We can now reflect this curve in the x-axis. And so we now have a sketch of both of those curves on the same set of axes. The second part of the question asks us Giving a reason, state the number of real solutions of the equation x minus 2 squared times x minus 3 times x plus 1 is 1. Again, that's not an equation that actually showed up in the first part. We'll see in a moment if we can work out how we can do anything with this, but first of all, there's one extra detail here that might be important. This question asks us to state the number of real solutions of the equation. We've seen this kind of wording before, so I'll remind you of the advice I gave you then. If you know why we're talking about real solutions rather than just solutions, well done you understand what's going on here. If you don't, you can just ignore that word. It just means, as far as you're concerned, how many solutions have we got. Now, how do we deal with this equation? I think we should have a reasonable expectation that this is something to do with the intersection of the two curves we've been working with. So what would happen if we did look at the intersection of those two curves? Well, that means we would be looking at the points where the curve y equals negative x plus 1, x minus 2 squared intersected the curve negative 1 over x minus 3. And now you can see that if we multiply both sides by x minus 3 and also by negative 1 to get rid of the negatives on both sides, then we will have x plus 1 x minus 2 squared, x minus 3 is 1, which apart from the order of the factors is the same as the equation we're being asked to look at. So therefore the number of solutions to this equation is the same as the number of points of intersection of our two curves. Returning to look at our curves, we can see that there will be 2 points of intersection. Again, it doesn't matter if our graphs are drawn absolutely perfectly. Because we understand their general shapes and their positions with respect to each other, there can only be those 2 points of intersection. So our final answer to this question would say that because there are 2 points of intersection, that means that the equation has 2, and if you feel you want to write the word real, you can do that, 2 real solutions. Notice in this case we weren't asked to find those solutions, and in fact that wouldn't be a particularly easy thing for us to do. But in many of these questions you're just expected to use your knowledge of graph sketching and intersections and how they relate to equations simply to state how many solutions those equations will have.